You're listening to a UC San Diego podcast.
Okay, so let's get started. It's 3 o'clock. 4 items on the agenda today. Item 1, as always, is any questions anybody has left over from last week. We're hoping the audio gets recorded today, please. Okay, so that's 1. Item 2 on the agenda will be presenting Lab 3, which I have put up on TED. Item 3 on the agenda will be Verilog, basically Verilog lessons in more detail, looking at specific examples of writing Verilog code from scratch and designing various useful things that may help you out in some bizarre set of circumstances, such as Labs 3, 4, and 5 in this class. And then the 4th item on the agenda is, let's see, we've got the Verilog, going over Lab 1. If there's anybody that wants to go over the Lab 1 solution with the alarm clock thing, I'll be glad to show my solution on that. So those are the 4 items on the agenda, presumably in that order, unless somebody wants to change anything. So item 1, does anybody have any questions about what we covered last week, about the ongoing assignment? We've got Lab 2 going. The TAs are grading Lab 1. And then, so any questions at all before we dive in on what Lab 3 looks like? Everybody at least made a start on Lab 2 at this point, I hope? Okay, this is a good time to start. So remember, I gave you till Thursday of the 2nd week for Lab 1, but I have to start pulling that in because I can't go Thursday after finals week for Lab 5 because I have turning grades Tuesday. So realistically, I have to start shortening the due dates. I gave you extra time on Lab 1 to get spooled up on the tools. I gave you extra time on Lab 2 because we've had problems with the podcasts and everything. So, all right, let's go ahead and look at Lab 3. So there are going to be 2 parts on it. And the first one is going to be, for those of you that have looked at this problem before, maybe last term if you took 140 from me, or in other classes you may have taken, this is your classic traffic light controller problem with a couple of wrinkles. So what we have is we have 2 intersecting streets at right angles, and we're just assuming we either have a green light for the east-west street or a green light for the north-south street. And then what happens, it starts red for everybody. Then if somebody drives up on either the east-west or the north-south street, it will then change to green for that direction. And we hope it stays red for the other direction, okay? You've got to be responsible civil engineers on this stuff. You don't want to get sued. So you got to keep the other direction red, turn green for the where you have cars detected. If you keep getting a string of traffic, I'm going to give you a test bench. I'm going to either tell you there's traffic or not. So the idea is it turns green if there's a car there to trip the wire. If there's another one right behind it, another one right behind it, it will stay green for a period of time. But I do have a timeout, so even if I give you a whole parade, eventually you'll need to cut them off to yellow and then red. So the idea is as soon as the traffic goes away or as soon as we reach our maximum count, we change from green to yellow. We stay on yellow for 2 cycles, and then we go to red. Then and only then, when everybody's all red, most modern traffic lights, we have an all red period for 1 second where they've turned red and they haven't turned green yet. Then what we'll do is as soon as we see traffic the other side, we'll turn green for them. Works exactly the same. Green and then either run out of traffic and count down to yellow and go to red, or we still have traffic, we time out, go to yellow, go to red. So I'll give you the test bench. We'll go through. It basically tells you there's traffic north-south, then the traffic goes away, then there's traffic east-west, traffic goes away. Then I make it more entertaining, and I have traffic both places at once. And then what I stipulate is if you have people coming at the same time, we are prioritizing so the north-south gets the green light before the east-west does. So in case of simultaneous arrival, we're giving preference to the north-south. We're not giving them both green at once. Again, we don't want to be sued. We want to do this right. So that's basically what you're doing. I'm going to give you the test bench. And what you're going to have to do, what I suggest first, is take my description of the problem and write out, maybe a diagram or something of what the state machine ought to look like. How many states do you think you need? How do you want to deal with that? Once you've done that, then you're going to write the Verilog code based on your state machine. I'm going to do an example of that today. I'm going to do a different example today. Don't ask me to do this one. I'll do a different one. But I will show you a couple of state machine samples today, take you through the whole thing. It's pretty simple, show you how you set them up, how you go through that. Then once you've made your state machine, then you run it and submit your code, submit your screenshot showing the red, yellow, green, and your screenshot showing the transcript, which will say red, yellow, traffic, green, yellow, red, traffic, green, yellow, red, whatever. Okay? So that's what we're going to be doing for Lab 3. Second half of Lab, there's more. Second half of Lab 3 should be probably easier of the two. It's just going to be making a little pseudo-noise generator. And what these are, this is also called a linear feedback shift register. This is the fundamental basis of almost all modern security codes, one way or another. So if you just look up LFSR, linear feedback shift register, and you get pictures of it, and it looks like that. Isn't that entertaining? And let's make that a little bigger. That's ridiculous. This, ladies and gentlemen, is a linear feedback shift register. Ours is going to be 8 elements. Each of these is a D flip-flop, each of the squares on top. And the way it works, the way this one works, this one shifts to the right, ours is going to shift to the left. But basically what you do, remember last lab we had a shift register that could either do a logical right shift or an arithmetic right shift. We had to play with whether we keep the sign bit or not. This is similar, except instead of worrying about shifting in a 0 or a 1, we're going to shift in a well-defined parity function of select bits. So what we're going to do, here's our state. State is whatever 1s and 0s occupy our register. Every time the clock ticks, next state replaces, state updates to whatever next state is going to be. Which means in this case, it's Mad Hatter Tea Party, clean cups move down. Everybody does clean cups move down by 1. So this 1 goes to here, this 0 goes to here, this 1 goes to here, this 0 goes to here. Then what goes in the front here, and again ours is going to work the other way, but same idea. I'm going to I have what's called a mask, and the mask is going to pick this guy, this guy, this guy, and this guy. Take the parity or exclusive OR of all 4 of those. And remember, what's the parity? If I have 4 bits and they're all 0, what's the parity? If they're all 1, what's the parity? If there's an odd number of 1s, what's the parity? Okay? So it's just going to tell us whether the number of 1s that we're feeding back, we'll be feeding back 4 of our 8, whether there's an even or odd number of 1s among those 4. And if it's an even number, we feed a 0 in. And this will be our bit 0 down here. This will be our bit 7 up here. We're not going to have 15. But here's our bit 0, our bit 1. So we're going to be doing what's considered a left shift. The picture is misleading because it numbers things left to right ascending. And that doesn't make sense for binary arithmetic. We always put the least significant bit on the bottom. So we always put bit 0 down here on the right, bit 1, bit 2, bit 3. That's convention because that's what works nicely with arithmetic. So we will be left shifting. even though this picture confusingly is right shifting. But the numbers are backward, so just mirror image this thing. You get the idea. In fact, maybe we can do that. Oh well. Anyway, so that's what we're doing on this guy. You're going to have to build a linear feedback shift register. I'm going to tell you, I'm going to give you a mask function in my test bench, which will select which 4 bits get XORed together. You have to make them shift in. Again, it's a very simple state machine. Simpler state machine than the first problem with the traffic control. Okay, and then the only other thing you have to do, I'm giving you the whole, on the traffic, I'm giving you the full test bench. You do not have to mess with my test bench at all, just use it. I'll bring those up shortly and show you. For this one, you get to mess with my test bench. Keep what I have. I'm not going to mislead you, it's correct as written, but what it doesn't do, the other thing I ask you to do with the PN generator, I have 8 elements, okay? So this picture here, this here picture, where's that there picture? There's that there picture, okay? This one has 16 elements. If I have n bits of register, n elements, 16 here, 8 in our case, how many different possible states do I have? How many different binary numbers can I make? If I have 8 bits, I can count from 0 to what? It's the biggest number I can make with 8 bits. Unsigned. Don't worry about 2's comp. Just unsigned, I can go all zeros is 0. 255, and how'd you get that? Perfect, okay. So there are 256 possible states if I have 8 bits. Here there would be 65,536 possible states because there's 16. So we'll be having 8. So we'll have 2 to the 8th. The thing about the insidious property of these LFSRs, remember I said you're taking the parity, and parity of any, if you take a parity of a bunch of bits and they're all 0, what's their parity? Still 0, right? So if I start with all zeros, what happens? If I had zeros on all these feedback positions, if I had zeros all the way up, so I reset to 0. Say, hey, I know how to reset. I'm resetting to 0. Put it all 0. Then the first clock strikes, and what happens? My new bit shifting in is a 0. Everybody shifting down is a 0. What's my next state? That's a little boring. So LFSRs always have this property that the maximal length, the best you can do of a non-repeating sequence before it starts repeating again, the best you can do is 2 to the n minus 1. You can't do the all 0 state. You can do all the others. So what I want you to demonstrate in your test bench is that you indeed have achieved maximal length and you have all 255 possible states. So we'll look at that. So that's the only other thing you have to put into your test bench. And I'll give you some tools today that'll help do that. So those are the 2 things you do. That's lab 3. So traffic control and then an LFSR. Incidentally, if you're talking to the cell phone tower and you've got a conversation, somebody else has a conversation, how do you keep from eavesdropping? How do you keep from talking over them? In the bad old days, early days of landlines, they'd sometimes have shared resources called a party line, and people, particularly rural areas. And so if you picked up the phone, somebody else could be having a conversation on it. Well, with wireless, that's not going to work really well because we're all on the same piece of wire, all in the same atmosphere. And so what we did with wireless, the way they do it is they have these pseudo PN generators. Instead of being 8 bits long, they're 15 bits long, and the main channels are 43 bits long, 2 to the 43rd combinations. And so what happens is my conversation gets what's called spread or encoded with a particular combination of bits. Somebody else's is somewhere else in that rotation, so we're mutually orthogonal, etc. and so you can have multiple conversations on the same cell phone tower. So you ever wonder how they do that? This is what's behind it, except that we use more bits, because with 8 you wouldn't have a lot of variety, and you couldn't have a lot of different people on there. Also, this is what's used on your garage door opener or on the remote on your car, so that every time you open it up, this thing advances. So the next time the code is different. But your garage door knows that, and your transmitter knows that, because they both advanced. And then these guys that do the hackers, they get into your, I think I talked about this one of my grad students last quarter for their term project. They build a device, well, first of all, they build a device that works the same way the hackers do. So what it does is you try to open your garage, you set up a PN code, whatever PN code is current, comes transmitted out bit by bit. It just reads out what's that value, bang, 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 bang. That's the signal it sends. Garage door opener normally would see that and respond and open. Oh, that's a cool code, I like that. So they jam it. They eavesdrop on you, and they send out a jamming signal so your garage door never gets the message. Then what do? You press again. You just say, oh, I blew it, right? Meanwhile, they've recorded your first message. Now they jam the second one too. Well, they don't jam, what they do is they jam the second one and record it, and they transmit the first one, and the door opens, and you think everything's fine. You drive off, close it again, they record that one. Then they have the last message you ever sent has not been used yet. They've recorded it. They wait till you drive off. They come over, and they use that message and they open your garage door. So my students built a cell phone app. So when you drive out of your garage, use the cell phone app to turn on your own jammer. Anytime somebody tries to open your door, it jams their signal and it won't open, including you, anybody. Then when you come home, use your cell phone app to turn off your jammer. Then you can do your normal operation and get in. So that was they called it a Guardian after our school paper. So that was the Guardian project. And you look up RollJam on the internet. RollJam is the hacker thing that people use. So that's how people break into garage doors or Toyotas or various things, because Toyota uses a pretty wimpy rolling code. So anyway, so this stuff is, as I say, this is pretty fundamental to security and to different channels on cell phones. It's got a lot of good uses. So you might as well know how the things work. Okay, so those are the two assignments. Let's see if there's anything else here. So for the turn-ins on this one, working code, my test bench augmented to prove that you have a 255 cycle repetition. If you want to have some fun, take my masking function, which is which 4 taps I choose, turn it around. And instead of getting 255 states, you'll get 217. You won't be able to hit all the states. It's not a maximal length sequence. There's only certain ones that are. So it's just kind of a fun thing. But the main thing you're doing in the test bench is you'll run it, and then you'll have to have a counter of some kind that's going to detect. I did reset. And when I do reset, the PN generator goes to 11111 all the way across. Then I run it, and I want to sense when it comes back around again to 111111. Then I'll set a flag at that point and count how many cycles it's been. Just see a counter in there, a little detector. It's very easy. So that's what you're doing for that. So what am I giving you? Give you all kinds of helpful stuff. There's my helpful stuff for the PN generator. Isn't that helpful? So all you have to do is, I did the hard part. I got all the I/O stuff on there. All you have to do is fill in the guts. But this is just describing a little shift register. It shifts some parity feedbacks. You can find this stuff all over the internet. It's real easy to find examples, so go ahead and do that. Let me know if you get stuck, but I don't think you'll have trouble with that. And then here is my test bench. And it works fine as is. It's going to go through 3 cycles. This is 800 clock cycles long. So it's going to go through 3 cycles of 255, hitting FF, hitting FF, hitting FF. So that part's fine. You just have to add your own counter in here somewhere to count how many cycles between the FFs. And I'll show you how to do Superman X-ray vision today so that you're saying, well, wait a minute. This is up at the test bench. The test bench doesn't get to see what's down inside the pseudo-noise generator, the PRBS. All it can see is the 1-bit output coming out from the PRBS. But I'll show you how you can use X-ray vision to look down inside any submodule. It's very, very useful. You're in a test bench. You can use this dot hierarchical notation. I'll give you an exact example today, go through it. And this lets you look down inside anything. Or we have our other weapon, which was our waveform viewer. And that lets you look down inside anything, as we've seen. So one way or to other, you ought to be able to see whether you've had the repetition that takes all 255 states. So that's what we're doing. That's lab 3. Let me do one other. I think that's probably, so any questions, either about the traffic lights, you've got simple state machine, there's 2 different sensors, there's 2 different sets of red, yellow, green. They need to be coordinated because if one of them is on yellow or green, the other one better be on red. I also want a state in which everybody is red. I want an all clear state in between. And then the other one can go green, yellow, red, and the other one has to be red. And I give you some timings on them, so you have to decide, how do I want to handle the hardest part on the first half of the lab is how would I like to handle the countdown problem, the fact that I need to max out at 5 cycles and change to yellow, and yellow has to last for 2 cycles. How do I do those sorts of things? You can brute force it by making more states. Just say, I got to walk from this state to this. This is green 1, green 2, green 3, green 4, green 5. Now I can go to yellow. You can do stuff like that if you want. You can brute force it, or you can put a counter in there. If you're new to state machines and uncomfortable with it, just try brute forcing it. I'm not restricting you on how many states you can use. So if you think you need more states, go ahead. I'm not going to make you be efficient on that or anything. But the whole idea is you got a state machine, and we're going to be doing some examples next in class. I'll go through some code. I got a couple of sample state machines that I think will be helpful on this. And what you do with a state machine, you've got a current state. You have always a pause-edge clock. And what happens when you hit the clock? Whatever the computed next state ought to be now becomes the new current state. And then that new current state is combinationally used in some functions to figure out what the next state's going to be, maybe often in conjunction with the input. And then those decide next state. The next clock hits, that new next state becomes the new current state, and that current state, in conjunction with the inputs, determines what the next state's going to be. And this is how they all work, and I think it'll be clearer when I show you some very explicit examples of that. Okay, so that was the second thing I wanted to cover today. And then the third one is looking at some sample code. And I've got some resources that I have put up on our, so if you go here, this is the content lectures part, week 3. And you'll see Altera State TB. This is a test bench for a little state machine that Altera provided on their website. I had to clean it up because they didn't do it right. Anyway, so I did. They had their blocking and non-blocking screwed up, which amazed me. We'll go through that today too, make sure we're clean on that. Then I've got this Verilog PPTX guy. And I got Verilog exercises. I got these 2 PowerPoints. I got these live examples. So I'm going to start with the 2 PowerPoints. Let's look at Verilog exercises here. This is pretty good. So there we go. Okay, these are self-paced. So what you can do, we'll go through these entire things today, but I encourage you kind of work through them on your own. This is how a state machine might work. This is a typical logic block. This is not a state machine yet. And the reason it's not a state machine yet, in order to be a state machine, I'd have to take, this is current, these are registers, D flip-flops, always at positive edge clock, Q equals D, bang. So this is my current state. In order to have a state machine, I would have to take my current state and wrap it back to my input and have some function of my input and my current state to figure out my next state. What this is right here, oh, and this says possible state feedback. So that's what I'm talking about. Take the current state here, bring it back around into here, mix in some other inputs, like is there traffic? So this says, what's the current status of my traffic signals? Well, I got green for the east-west, and I got red for the north-south or something. And then this is saying, oh, we have traffic waiting for that red light on the north-south. So we better, for our next state, consider making the other guys advance to yellow and then to red, so that we have the opportunity to go green and be polite and let this guy go through instead of sitting there all day. So to make it a state machine, I need this. That's what this possible state feedback, that's precisely what that dotted line means. If I'm not doing feedback, if I'm just working on a stage of something, this could be a combinational adder or something, and then I'm capturing the sum or the result and then passing that to the next stage. This is also very commonly done, in which case there is no recursion or feedback. But for a lot of stuff we're doing, there will be some kind of a recursion. If this was an accumulator, this would be an adder. This would be the number I'm accumulating. The accumulation would be forming here and would feed back each time to get added to the next new guy, and I get a sum of terms this way. So I keep bringing in a new term, add it to whatever was already, take what was already there, that's my accumulation, add my next term to it, that's my new accumulator value, bring that around, add my next term to that, that's my new accumulator value, and I can accumulate some of a series of numbers. So that's how I could use this. Or I could just simply say A times B plus C and store the result. And when I store the result, I can now start working on the next A times B plus C, a new set of numbers, and then store that result and work on a new set. And that's just called pipelining, where I just run things down a clock pipeline. So, guidelines. Always at pos edge clock. This is the only way that Verilog knows that I want D-type flip-flops, I want so-called sequential or clock logic. I want these guys over here. This is the key keyword. Not CLK. I can call my clock grape. The language doesn't care. There's nothing special about CLOCK or CLK or put it in some other language. There's nothing special about that at all. There's something very special about this guy because that's a keyword. If I just wrote always at clock, that would mean anytime clock changes, high, low, whatever. That's more of a combinational flavor. So if I want sequential or clock logic, absolutely mandatory, everything in the sensitivity list inside this paren here has to be either pos edge or neg edge, everything in that list, no exceptions. Then the other thing we do is we use this non-blocking form, and the cool thing about that is this is telling the simulator to act as though all four of these are happening simultaneously. Even though as computer scientists, you know you may only have one thread going, or if you're taking my graduate class right now, we're doing multiple threads on GPUs, but let's assume we've only got one thread or maybe two threads, dual core or something. I can't possibly compute all four of these at the same time. But what I can do is I can simulate although that was happening. So what I do is I look at the right-hand side of this guy here, and I store that in temporary. Look at the right-hand side of this one, store that in a different temporary. And this one, and this one. So I store all four of these intermediate results in their own respective temporaries. Then and only then, I apply those temporaries in any order to the targets on the output on the left. And by doing that, the neat thing is I can put these in any order I want. And it acts as though they're all simultaneous anyway. Non-blocking. This expression here, the execution of it, the D3 out assignment, this guy down here does not wait for that. He gets launched at the same time. That's what's meant. And this is essential. If I've got always a pause edge clock here and there, I've got clocked registers all over my design. I got a complex system on a chip or something. They all have to strike simultaneously. This is how we guarantee it. Combinational is the other type of logic. And for combinational, this is where you use always at star or always comb. So here's our first example here. This guy is what we're looking at here, this is a 2-bit, they call it a shifter. I'm just going to say it's a operator of some kind. It's not clocked. In fact, it says purely combinational. So what do? We have an input called S, and we have maybe this is a current state, maybe this is just a 2-bit input. We don't know if this is fed back or not. So let's just say this is a 2-bit input of some kind. So what does this mean here? I invert S, I AND it with the lower bit of in, and that's going to be the new out 0, the new lower bit of out. For out 1, it's going to I select either in 1 or in 0 depending on whether S is 1 or 0. Right, so if S is 1, I take the lower bit, and that becomes the new upper bit. That's the shift thing they're talking about, I guess. If S is 0, then S prime is 1, and I take the upper bit and feed it straight through. So this is just a 2-to-1 selector for to drive the upper bit, and it's just an AND gate to drive the lower bit. And this is how you write it in Verilog. So there's my upper bit with my select. It's either if it's either S bang or tilde S or S bar, if you will, within 1, or it's S true logic within 0. That's just my selector there. There's a logical OR between them. And then this one is just a logical AND. So that's straight combinational. Row decoder, we've looked at these a little bit. This is how every memory, your DRAM, your SRAM, your SDRAM, your DDR4 RAM, all that stuff has this in it. And the reason is memory works by having what we call word lines. If I have a 1K RAM, 1K byte RAM, I have to have 1,000 different word lines. I don't want to carry a 1,000-bit address into the thing. So what I do is I carry a 10-bit address. And in this puppy, this decoder, those of you that took decoders with me last quarter, what the decoder does is it turns this condensed, shortest possible binary number into a 1 out of n expanded number. And that's what this is doing. This is taking 3 bits in as address. It lets me select any one of 8 rows. So the logic to do it, this is all you have to write. You don't have to do any Carnot maps, don't have to do any optimization of any kind. This will do it for you. So the tool will handle that. And so all we do, it's really simple. We just say, okay, for these 8 different possible values of our address, the binary number coming in, we have 8 possible acceptable outcomes, 1 in each of the 8 positions for the output. That's all you have to do. It's combinational. We have an enable on it, so if we're not enabled, they're all turned off. The enable is really cool because now I can have multiple banks of memory all on the same bus, and if I have the enable turned off, this particular memory will not drive the bus or will not get recorded or written onto from the bus, and somebody else, some other memory chip on the same bus can do it. So let's suppose I had a 4-bit address. The 3 lower bits tell me where I am in this memory block. The top bit tells me, am I in this memory block Or am I in an identical memory block over here? So 4-bit address, the top one picks which bank, the bottom 3 pick where I am in the bank. Expand that up to 10, 12, 32 bit, 16 bits, whatever number you have, the principle's the same. This is why you see these memory sticks lined up, or you see a big backplane and you see a whole bunch of memory cards plugged in. That's how that works. You can pick the enables differently using your upper addresses. Okay, so here is, this one's kind of useful as well. Here's an 8-bit parallel register. It's not a shift register, it's not serial, it's a parallel register. We bring in 8 bits, we bring out 8 bits. But the characteristic of this one, it has a reset, it can either, and it also has a load enable. So on every pos edge of clock, if the reset's true, this guy goes to 0. If the load is true, whatever the current value is here, it takes a snapshot of that right at the pos edge clock. That's the new Q. If I'm not loading, whatever Q was just gets recycled and held. So this is one way of building an enable. So this is a load or enable control, and then the reset's done separately down here. Okay, so that's another way that works, and this is what it looks like. So always a pos edge clock. If reset Q is 0, else Q next, and Q next. So this Q next guy right here, load question mark DNQ, that's this right here. So any questions on those? So this is some fairly basic blocks. You've probably seen variations on those. So let me go, let's up our game. Yeah, please, sir. This last slide, this one right here. Yeah, Q next. Actually, excellent question, because anytime if load is high, anytime DN changes, Q next is changing. But I'm ignoring it. I'm ignoring it until there's a pos edge clock. So this is like a camera shutter. The way this works is this guy could be changing all over the place, and then right at the pos edge clock, the last, musical chairs, right? The last value we had, we stop, that's what we take. Now that gets into the whole issue, which we're not going to do in this class, but ECE classes, we talk a lot about metastability and about what happens if this guy is still changing right while I'm trying to take its picture. What happens in photography if your shutter speed is a little slow and your subject is a little fast? What happens? You get the same thing here. And the way a blur manifests is I can't tell it's a 0. I'd like to have a 0 value or a 1 value. We know that you have to be able to transition between them. So I caught it somewhere on that slope. Maybe it rounds to 0, maybe it rounds up to 1, maybe it comes out right metastable, which is what we dread, but it can happen. So that's why we put a requirement that there's what's called a setup time and a hold time. We just say that this number has to be stable for a setup few picoseconds before the pos edge clock and remain stable for a picosecond or two after pos edge clock. We have to have a nice stable or not very rapidly changing thing right when we're trying to take its picture. But yes, Q next could change any time. Q cannot change just any time. Q changes one clock to Q propagation delay from that register, which is usually a fairly short number. Excellent question. Okay. So let's look at another example. See what else we got in our bag of tricks. So let's look at this guy. Verilog tutorial. Oh, this is the, yeah, I don't think I'll pull this one up, but this is all from ASIC. This guy just cribbed all this stuff from ASIC World, so you can get it on their website anyway. I don't think it's going to help us as much as this other stuff, but I did include it. Anybody wants to look at it. This one's probably more valuable. So let's go ahead and look at this guy, make it a little bigger. 78% doesn't cut it. Let's see if there's room. That's better. Okay, so what we have here, I made a PowerPoint of that. Let's open that up. Yeah, let's do this instead. This is my cool PowerPoint version of it, so we'll see if this works better. Oh, okay. Nice when things work. Okay, don't worry, don't get lost in the weeds here. This is a big microprocessor, do not worry about that. If you take 141L from me next quarter, you'll get sick of these by the time we're done. So don't worry about it yet. The main thing is focus on the Verilog itself. So this is how we use Verilog. We can write a top-level behavioral model. We can write it in C. We can write it in Verilog. Register transfer level, that's what we've been doing. Always at pause edge clock, always calm. That's all the stuff we've been doing, the more structural looking Verilog. And then gate level is what Quartus does. And I don't make you write gate level logic because we have all these neat tools that do it. So why put you back in the Stone Ages? Early Cenozoic, we had to write our own gates and stuff, but you don't do that anymore. Okay, so this is writing synthesizable Verilog. Combinational, use the equals, the blocking equal sign, rather than the non-blocking that we looked at. And this says always at star, which is the old way to do it. Always underscore comb is the newer way to do it. They both still work. All the old stuff, here's the thing on system Verilog, which is what I teach, versus regular Verilog. Almost everything that worked in regular Verilog still works in system Verilog. Type reg, which I never use, still works. Always at star still works. The exception is that we've added 300 new keywords. There are only 100 keywords in the regular Verilog. There's about 400 in system Verilog. So if you were unfortunate enough, and I've done this, don't ask me how I know, but it's very painful. If you have used one of the new keywords as a variable name or a module name or something else, you're kind of in trouble when you do system Verilog. So that's the only place it's not portable, is if I accidentally used what's become a new keyword. So you just have to watch out for the keywords. One way to protect yourself against keyword plagiarism, I haven't been doing this consistently in this class, but it's probably not a bad practice. Every time you name a variable, every time you name a module, use initial caps, because every keyword in Verilog is all lowercase. So if you put lumpy capitals, all capitals, initial capitals, anything at all like that, then if you accidentally use a Verilog keyword, the capitalization will save you because it won't be the keyword. There's a difference between LOGIC, all lowercase, and capital LOGIC. Verilog is case sensitive. VHDL isn't, that's a whole other story, but Verilog is case sensitive. Okay, so every variable should have a default value, because the problem here, the gotcha for combinational logic is that if combinational means that it has to be driven constantly by its inputs, it has no memory, it has no retention, it has no ability to hold a value. And if I set this up so that I have an incomplete sensitivity list, I could end up having a problem where certain changes at the input the simulator doesn't respond to, because it says always, if I do something like always at A, C equals A plus B. If A changes, great, C gets reevaluated. If B changes, C does not get reevaluated. I'd have to do always at A or B, or do always at star, which does that for me, or always cob, which does that for me. So if I have ifs without else, if I have if, else if, and no final else, I have a case without a default. Anything like that, that's going to give me what's called an implied latch. So if you want combinational logic, your last expression, if, else if, there should be an else at the bottom. okay? Otherwise, you have the possibility that you're asking it to remember something. Then it's a latch and not a combinational. Or if I have a case, I do case 0, 1, 2, make sure you've covered every possible case, and just to be safe, put a default colon thing at the bottom, which is like a final. Because case is the same thing as if, else, if, else, if, else, if. So have some sort of a default on this stuff. Okay, here's we've already seen sequential logic. Non-blocking is important. Do not mix blocking and non-blocking in the same expression. You will be very unpopular. And then here's some example. Here's a case where we're going to bring in a number, we're going to add 1 to it, and we're going to add 1 to it again. But notice the timing implications here. If a new number comes in over here, it's going to take a clock cycle before we see it in here, take another clock cycle before we see it in here, take another clock, so 1 to third rising edge, we'll see it coming out. So it comes in before this rising edge, it'll come out after this one. You can map time across this space here. And so this is one way of expressing it, merging the combinational parts with the sequential. This is perfectly permissible code. The nice thing about writing it this way, I can put these in any order, it still works. This is another way of writing it. Some people prefer it. All I've done is I said, this is combinational. This is combinational. Let's put them in combinational type assign or always comb type expressions. And let's put all the sequential clocked guys into an always at pause edge clock. And that's what we're doing. And it's perfectly equivalent to the last one. This is what we don't want to do, always at pause edge clock, and I put this whole mess in there. And it's syntactically illegal. The Verilog police will get you. Get the blue screen of death. Your computer will crash. You won't be able to recover your hard drive. No, but it will give you an error message. Okay, another style, you could do it this way. Now this is what's totally cool about non-blocking. Now what I've done is I broke up that same non-blocking expression into 3 different always at pause edge clocks. It still interprets those as being simultaneous, just as it did back here. Not there, that's the wrong one, this one. So this one, all 3 happen at the same time on the stroke of midnight, pause edge clock. Here, all 3 happen at even though they're distributed differently, it works exactly the same. These are both perfectly acceptable. And then here's blocking. Will this synthesize? Yes. Is it correct? And if I wrote always underscore FF, which is the modern style, it would catch this and tell me you're being bad. So the always, you've seen me use always underscore FF, that's a linting tool. Always at pause edge clock, always underscore FF at pause edge clock are 100% identical in their meaning, but the always FF will catch stupid stuff like this. So, and then the rest is execution. So I'm not going to go into this here because I've got some better examples to show you. So anyway, that one's available for your amusement. And we'll go ahead and... okay, so I'll close that. And we'll close that one. Yeah, this up here, this would actually be a pretty cool state machine too. This is our ATM example. So you have your welcome screen. It says, put in your card. You put in your card, what does it do? What does it ask you for when you stick in your card? PW, right? Your PIN or your password? So what this does, every time you hit a digit of your password, it's going to collect that, wait for you to do the next one, wait for the next, and it's watching for what? Watch for the pound sign. When you pound the pound sign, it means you're done entering. Or when we try to get into buildings around here, sometimes you have to do that. And then at that point, what does it do? It compares that series it just stored against the correct password. And if it's valid, it's going to let you start your transaction, take you to the next screen. If it's not valid, it's going to say, try again. Maybe it goes 2-3 times around and then locks you. You have some websites, you try to guess your password a few times, it says you're locked out for the next 15 minutes, or you're locked, or you're out of luck, you know, you're SOL, you can't ever get your money again. It's locked up. Yeah, some of my discussion websites, they tell you can't get on again. If you get 5 wrong guesses on your password, you can't get on for 15 minutes. And then some of the bank accounts, some of the brokerages will say, you know, contact the broker and prove you're yourself because we're locking you out permanently. So it kind of depends on the website what they do. So let's look at an example here of a state machine. PRBS traffic. Problems, and let's open up. So here's a state machine. And this one's really dumb, but it's, I think, be helpful. So I stole this one off the Altero website, and I cleaned it up and corrected it because they had embarrassing errors that I'm tempted to gripe at them about. So what do we have? We have, very typically, every self-respecting state machine will have a clock input. It will have a reset. It'll have 1 or more input bits. So when this is a hint for those of you that might be wanting to design traffic controls for some reason. If for some weird reason you want to do a traffic light controller, the inputs would be the traffic sensors. And then the states would tell the traffic lights what they're busy doing. And so this is the other hallmark of a state machine, is to have a current state and some next state. This one also has an output decoder. So the way this particular, and it doesn't have to be done in a way, but the way this particular one works is I have a 2-bit state register, so I have 4 possible states, and always have the same number of next states as current states. And then what I have is I have a 4-bit output, and this is just a straight one-hot binary output decode. So this guy's just a decoder. If my state is 0, I put out a 1 in the 0 bit. If my state's a 1, I put a 1 in the 1 bit, the 2 bit, the 3 bit. So this is just a little decoder guy here. This isn't really part of the state machine, it's just what the output is. The rest is the state machine. This is just a convenience. I could use a type def enum, whatever I want to do, but here what I'm doing, rather than remembering, it's not real hard, right, that 0 is 0, 1 is 1, 2 is... But, you know, consider that these might be red, yellow, green, or these might be idle, run, reset, whatever. You know, you have a state machine, and you want to have some meaningful names for the states. This is your big chance to do it. So the design itself works in binary numbers. It thinks in terms of, well, these are decimal, but it thinks in terms of 00, 01, 10, 11, whatever. And then I'm just assigning names to them for my own convenience. And all the tool's going to do is every time it sees Zorro over here, it's going to say, oh, 0 is 0. Okay, so I'm just thinking 0. And every time it sees 1, it's going to map it over to here. Or that's what you meant. Okay. So I could call these grape, apple, pear, wouldn't matter, right? Yeah, if I'm making slot machines, I call them grape, apple, pear, whatever, and I can have different states. Okay, now here's the state machine itself. This is the no-brainer part of writing a state machine. So your traffic controller should have something like this in it. On reset, we're going to start with the all red phase. And then we're going to figure out, that's another story, what our next state, you know, who gets the green, what's our next state transition going to be, or do we stay all red? That's happening separately. But whatever we figured out our next state is, next time the clock comes along, my next state I've just figured out becomes my new state, and then I compute from there. So every self-respecting state machine has one of these guys, which is the register part, and one of these guys, which is the combinational part. This is where the real action takes place. So what does this state machine do? Anybody? Look at the always comb thing there, the case, and tell me what you think this guy does. What's the behavior of this guy? Or does it, maybe it misbehaves, I don't know, but what behavior do you expect here? Start at 0, what happens? Next clock it should go to 1, right? I'm at 1, what happens? We don't know because I didn't tell you what input is, right? So I could either barf back to 0 again, or I could go to 2. And then once I'm at 2, there's no stopping me, I go to 3. I'm at 3, there's no stopping me, I go to 0. I'm back around again. So there's only 2 possible operating modes. If the input's high, I'm going to do 0, 1, 0, 1, 0, 1, 0, 1 forever. And if the input's low, I'm going to do 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. That's all it does. So we write a test bench for it, which I just happen to have. So I came up with a little test bench for this puppy. And this is where I want to show you this cool feature here. So what I'm doing is I would like, I can always use the waveform viewer, but I would like to dig down inside. Just clean this just so I can fit everything on the same screen here. Doesn't affect anything. Oh, I can move this over. Good. All right, so here's my state machine over here. Here's my test bench over here. What name did I give my state machine? I gave it this instance name right here. Its type is Altera underscore state, because I got it in honor of the Altera website where I cribbed it. And so this, I've declared a new type. Just like wire or module or logic or reg, I've declared a thing called Altera state, which is this blob. So I instantiate exactly one of those, and I give it this instance name, and I say that every input is going to hook up to a connection wire with the same name. So its input list is clock in reset. That means clock hooks up to my clock at this scope. So this clock at this scope and this clock at this scope, those are 2 different signals. This says they are connected together. That's what this kind of, otherwise I could have written dot clock paren clock, dot reset paren reset. That's what this means. And then out is it's a 4-bit wire. Isn't that convenient? It's a 4-bit wire, connects here. And what I'm going to do is I'm going to display, every clock cycle, I'm going to display what's happening over here. And what this does right here, this one's easy. It displays what reset is. Big whoop, reset's available for me. So I can easily show whether it's a 1 or a 0. I change it, I start at 1, I change it to a 0, I bring it up to a 1, bring it back to a 0. So I can observe reset quite trivially because it's already in my scope. I would like also to observe, and maybe you would like to observe your PN generator. Just a thought, random thought for homework 3. But suppose you wanted to. I can't see the state at the top level because that doesn't provide me with the state. Now, if I'm a good detective, I can figure it out. It doesn't take Sherlock Holmes to say, well, there's only 4 states, and they look like 1, 1, 1, 1 on my decoder, and I can figure out and deconstruct what happened. But suppose I had multiple states mapping to the same output, I couldn't necessarily find out what state I was in, which will be your problem in homework 3. So how do I do it? I look at the waveform viewer, perfectly legit, or this diagnostic print statement, we call it display in Verilog, but it's diagnostic print. What it says is drill down inside AS1. Oh, there's AS1. Drill down inside it and look for a thing called state down in, oh, there it is, down inside it, and then display whatever that's doing. So now we have, this is what I call X-ray vision in Verilog. So I'm just walking down the hierarchy. This is the included content inside. I have a top-level module, which is my test bench. I've got my device down inside it. Maybe I have sub-devices down. I can go down as far as I want. If I had sub-modules, if I had like Russian dolls, right, you keep building them up in layers, I could go down, I can drill anywhere I want with this technique. Same approach. Dot this, dot that, dot that. Just drill down the hierarchy. Here all I'm doing is I'm just going down one level, and this way I can look directly at what state's up to. And then we run this. So let's see if this works. All ye of little faith, we will find out. Oh, that's traffic. So let's go to new. I think I already did a project on it. That's fine. Let's make a project from scratch. Go through it. It's good exercise. New project. And we're going to call it, oh, it's in problems. So I navigate to the directory with all, unless I want to deal with paths, which I may if I wish to. I don't wish to. So I navigate to the same directory folder that holds all of my source code, and I'm going to call this guy class demo 3. That's the name of my project. Add existing, and we want, oh, and it's not there. So it's up here. I blew it. It's under here. That's fine. We can navigate around to it. So Altera state, there it is over there. This just means that all of my work files, waveform viewer files, output files will all be in where I was originally. And then that's looking to my source files. But that's okay. It'll work. Otherwise, I should have re-navigated to where I was. Compile all. Share a little secret here. I don't have any real dependencies here, but sometimes you will. If you get any red X's and something isn't compiling and you think your Verilog looks pretty good, one little trick to try is compile order, auto-generate. And what this does, this way the tool will automatically go through, identify hierarchies, identify dependencies, resolve all of those before attempting to compile everything. In this case, I didn't need to. It worked fine. And most of these you won't have to, but I just wanted to mention that. Start sim, you always look for your test bench, which is here. And then let's go ahead and open up the, let's set up our waveform viewer as well. Add wave. And go down inside our device and add wave as well. And now we're going to run. And it stopped, which is a good thing. And let's see what we have. So what do we have? We've got a bunch of numbers. All right. Peel this over so you can see what's going, see some names of stuff. Nice to know what signals you're dealing with. I got a redundant reset. I don't need to have 2 lists of reset. I got 2 lists of clock. I got 2 lists of in. I got 2 lists of out. Okay, so now I have a fairly unique list. Anything you delete, you can always get back anyway. And I'm going to zoom out a little bit. And let's see, what else would I like to do? Oh, state. Let's make it hex, just for fun. Don't have to, but we could. And let's zoom out a little. This lets us zoom out a little bit more. So let's see how the dog walks here. So we got reset. As long as we're in reset, we're surprise, surprise, in state 0. And our next state's supposed to be state 1. I get to state pause edge clock. Next state was 1. Now my current state is 1. Next state's going to be 2 because the input's low. Remember, if input's low, we walk 0, 1, 2, 3, 0, 1, 2, 3. And if input's high, we expect to see 0, 1, 0, 1, 0, 1. So we got to our first decision point. Next state so state 1's our decision point. We go to 2, 3, 0, 1, 2. It gets a little more interesting here. Now what happens is I'm in state 1, and you notice that my next state is a 0 up here. There's state 0. Okay, but I'm in state 1 over here. Instead of being a 2, my next state is a 0 now. And that happened because my input went high, and the way I had my Verilog code set up is when input's high, instead of going to 2, I go back to start. So this is go back to go. And if input had been low, as in the earlier set, I just march all the way around 0, 1, 2, 3, 0, 1, 2, 3. This aborts the count, sends me back to 0. This is very powerful in state machines. Our example of our ATM. I start putting in my numbers. Now, in the example we showed, you go bang, 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 and then hit the pound key. I could also, on a combination lock or something, I'm not waiting for a final pound key, I'm watching the combination as it comes through. And as soon as I deviate from the right input, it could throw it back to the beginning, let's try again or something. Or if I'm looking for a series or sequence. This is done in communications. If I have a comm system, I send messages in packets. The beginning of every packet, there's supposed to be a thing called a preamble that says, here's a new message. And it's a unique series of 1s and 0s that I don't use any other way except to say start of message, pay attention. Then that's followed by a header that says, this message is for you, and it's not for you. And so I have to, in my receiver, I'm constantly trying to correlate, watch for that preamble to come in saying, here's a new message. Once I see it, I start correlating on the header to see if this message is for me and other characteristics about that message. If the preamble starts and I get a channel fade, so I get a drop call on my, you never get drop calls, right? So you get a drop call on your cell phone or something. What happens often is that you started to send a preamble, somebody, and it got interrupted. They're trying to decode it, and then they got some bad bits because of fade or interference. They go back to start again, and then you have to retransmit, resend until it makes the connection. The cell tower, the infrastructure does a lot of that for you. Your phone will do a certain amount of that for you. If it doesn't make the connection, it'll keep trying to resend the sequence till it links up. It's doing a request, basically. The preamble is a request. And as soon as the preamble is properly decoded at the other end, they will send an acknowledge back to you, which will be another encoded message. When you receive the acknowledge, then you know you go ahead and proceed. So it's a request acknowledge, just like you have in any sort of software or hardware transaction. Okay, so that's how this guy works. And as you saw, when the input was high, we do indeed just, we're stuck in 0, 1 hell here, right? So 0, 1, 0, 1, 0, 1. And we don't get to break out of it until the input goes low. And then wherever we were, we start picking up the 0, 1, 2, 3 again. So the takeaways from this particular demo are how to drill inside something, and just a good general, real simple scaffold for how you write a state machine, or how to write a state machine, how to do all the coding for the combinational part and the sequential part. And as a little bonus, we threw in how to do a combinational address decoder thing. But you don't even need this part to be the state machine, right? These two together would give you a perfectly proper state machine. So I think then I've put all these examples up on TED as well under content lecture for week 3. So I suggest reading these. I suggest going through the ASIC World website and the other ones where I showed you some Verilog tutorials. So that, anybody else, any questions about general Verilog? I have one more topic I'd like to cover today. Anybody's interested, I'll show you my solution on lab 1. But any other Verilog questions? Is Verilog starting to make a little more sense to people, a little more comfort with it? I think the hardest parts are the sequential versus combinational logic. When to use blocking, when to use non-blocking. How modules work, how modules nest inside modules. I think those are some of the and then just how flow control in digital works in general, because it's a little different than what you might be used to with software running through assembly code on a microprocessor or something. Okay, so why don't we take a quick look at the alarm clock. And then, so if this is from lab 1, again, I'm getting on the TA's case so they can get your lab 1 graded back to you quickly. So I told them I'd like to have that before Wednesday's class, have your grades from lab 1. And if you haven't started on lab 2 yet, this is a great time to do so. Also, what we'll do Wednesday's class, it'll be discussion section. I don't have a lot of new material. So anybody wants to come talk about progress on lab 3 at this point. We can also, let's see, lab 2 will still not be due yet, so I can't talk about it, but we'll cover more Verilog cases of any interest. But let's go ahead and look at, as promised, let's look at our Strawberry alarm clock here. Alarm clock. Okay, good, here it is. So alarm.sv. Okay, so this is all I did for the alarm module here. Yeah, so anybody else wants to take off, you can, otherwise we'll go through this. So are we washing? Yeah, I don't know why we keep doing that, so let's go back to this. So anyway, so this is all you had to do for the buzzer. It's just looking for a match between what's the current time and what was my alarm time. And what's the match for the hours? What's the match for the minutes? If everybody matched, we have a buzz. Okay, so that's all we had to do there. And then I've got, let's see what else we have here. Type SV, alarm clock. So I've got all these. Okay, so this is the one that didn't have the connections in it. So what I asked you to do was how to set up all these happy connections in here. And so if we do that, we should have an alarm clock solution. Otherwise, we'll regenerate it here. How about that? Okay. So let's see what else we've got here. Okay, then the other pieces of the puzzle where we had this count mod 24. Okay, so this is a way of doing a count modulo 24. And so this particular thing, the percent means modulus. And you can set any modulus you want. The way it actually works in synthesis is it will detect this value, and you've got state equals next state and all that stuff, and you've got a combinational logic to figure out the next state. What this says, literally, is I'm building a counter. So normally, next state equals state plus 1, right? No brainer. But, exception, if my current state is 23, then always one less than this, then my next state's going to be 0. So I could, if I weren't lazy, if I weren't efficient in my use of tools, what I would have done is do this the hard way. Okay, so we're going to do this the hard way. So instead of doing it this way, what we could do instead is say CT out equals, and then what we do is we say CT out equal 23. And if that's true, it's a 0, else it's CT out plus 1, that's all we have to do. But that's what this literally does for me. Okay, so all your counters, either mod 60 or mod 24, they should all have some sort of thing like that in them. And there was another part of the lab I didn't assign, which was to make it into a calendar thing, and then you'd have mod 31 conditional on which month it is, mod 30, mod 28, but you can figure that out too. All right, so what else do we have here? So we've got the counters, display test bench. What this guy does is just looking at the segments. So this is just a different type of decoder. What this one is doing, I've got 7-segment display, 1, 2, 3, 4, 5, 6, 7 in a circle with the 7th one across the center. If I'd like to make an 8, I light up all 7 elements. If I want to make a 0, I light up 6 of everybody but the crossbar, which in this case is the bottom bit. So the least significant bit would be the crossbar. That's the only difference between making a 0 and making an 8 on a 7-segment display. So that's what that is. And then what this guy does, I've got bin 0 and bin 1. And the reason I have bin 0 and bin 1 is that if I want to change, I've got segment 0, segment 1. So I want to, and the difference here is I'm doing a 2-digit decimal display. So I wanted to do binary, what's called binary coded decimal. Normally binary works in hex, works in 4-bit 16, mod 16 stuff, and I want to map it into decimal stuff. So this is what's often done. This is going to give me 1 digit. This will give me the other digit. And the only difference is if I take the number I'd like, divide it by 10, floor. This is like doing floor of divide by 10. So if you're in C, this is floor of bin n over 10. No, it's not. It's the, that's not the divide, that's down here. I'm sorry. This guy is mod 10, this guy is just doing mod 10. So this is going to give me the least significant digit, LSD. Okay, least significant digit. And then this one here, this is going to be floor of divide by 10. So if I cleverly find the least significant digit first, subtract it, so I found 47. So I found the 7. Subtract the 7, I get the 40, divide by 10, I get the 4, that's how I get the upper one. So that's the basis behind that. And then we make the connections to stuff. So any other questions on the alarm clock? Everybody got that one kind of working? That looked pretty good. So that's kind of what's behind it. The other thing I did was, okay, display TB, and then we're going to go through. I have this little task that does the display thing. Okay, so I have my structural diagram, which was the top level, and that's over here. That's what I was looking for. So struct diagram.sv, which is right here. This is how I hooked everything up. So this is my solution here. I'll go ahead and post this guy up on TED for everybody. But here's my connections. I have a seconds counter. It's always enabled. It resets to 0 when I hit reset. It's pulsed. I assumed I had a once per second pulse coming in. It's clocked by that. Everybody's clocked by that. This guy's always enabled, and he puts out time in seconds. And whenever the seconds come back around to 0, he puts out a 0 flag. This guy is the minute counter. he is enabled once per minute, he's enabled once per hour. How do they get there? I need some logic that's going to tie those together, right? So that I can, so I have t-hen, th, and all that stuff. Binary in, so where did I put that? Ooh, this is not, okay, so I didn't finish that off. So this is what I had to decode. So tmem, this means time in minutes enable, had to come from two places. If I'm setting the minutes, this guy has to hook me up to pulse because I want to advance by once per second when I'm holding down the set control, which was this guy, SY, here it is. Here's time set, here's alarm set, and then here's minute advance. So if I have time set or alarm set, so if I have time set and minutes advance, both on, then that should turn on the minute enable. And otherwise, it depends on this S0 over here. So that's the sort of logic I need for those. And the same sort of thing for the minutes to hours. So that's what those all did. And then these were my display drivers, 2 digits each, so that I could put out everything I wanted. Okay, so anyway, that's what you needed on the alarm clock. So it's, probably most of you already got that. So, any questions about anything we've done today so far? Looks like everybody else is happily leaving here. So what we'll do, so go ahead and finish up your lab 2 because it's due Wednesday night. You have one more chance to attack me Wednesday if you still have questions about it. But try to really get a good, if you haven't already got a good go on it, try to do that right away. And that way you'll have more time to fix things up. And then get started on lab 3 as soon as you have lab 2 under your belt. And if you have questions on lab 2, you know, Piazza, office hours, between me and the TAs, we try to cover all week. I'll be around most of the day Wednesday, so see me before class almost any time. I'm in early, so come see me Wednesday or pop me an email on Tuesday if you want. And we'll get that covered. And I'll go ahead and post my solution. I have to find my exact solution. I'll go ahead and post it on Piazza here. But you got the idea on that. Okay, so have a good rest of your week. We'll catch you Wednesday. And get going on the labs. If you have any questions, let me know. Sir?
So this is like a really dumb question, but
No, it's not.
on all of last week.
Okay.
I was counting on the podcasts to help me.
And you didn't have any audio? Yeah.
So I actually went through it over the weekend. I looked through everything that was posted, but I'm still really confused. And I was just wondering if you could tell me where like the lab write-up is on TED because I can't even find that.
Okay, let's do some of that. Let's go through that right now. Yeah, I apologize for our IT crew on the audio thing. That was a total screw up. Anyway, so if we go down here, here's the, there's 2 things. So under content, lectures is going to have like all today's material and the stuff that you saw but didn't hear last week. And then back under here, if we go to labs, we got lab 1 and lab 2 here. We've got the assignment, and I've got the Robertsons, and then here is the exact assignment written out because I wasn't as clean on that as I like, so I fixed that up. So here's exactly what you need to turn in. Here's what you use for it, and then here is. So basically what you do is you unzip this guy. And you go through that. And what that's going to give you is, in fact, I'll just show you. I'll pull it up and show you. But it gives you a whole bunch of Verilog modules. And I'm doing the reverse. Lab 1, what I did is I gave you the stuff down lower pieces, and I had you stitch it together. Lab 2, we're taking the opposite approach. I'm giving you the top level and having you flesh out the details inside the different pieces. So if we go over to lab 2 here, and lab 2, let's find it. My bad, I've got it here. So on TED, it's under labs. I just stupidly have it under here. Don't mind me. Okay. So here's the assignment. Yeah. So for instance, I give you the add subtract module, and I just ask you to come up with the expression. So this is what it's supposed to do. It's a one input control. It's got to do these. So that one's pretty easy. And I do that. Let's just grab a couple others.
So for all these modules, we just have to make them expensive?
What you have to do, I give you the top level. So all you have to do is like here, I give you a list of inputs and responses. And you just have to write the Verilog code. In this case, it's a clocked logic. So you'll need non-blocking, all that stuff. And it depends, if clear is high, that takes precedence over everything. If clear is not high, then you look at load 1 or load high or load low and set up these guys accordingly. And I've got basically, the N is 16. So I have an 8-bit in low and an 8-bit in high, and I have a 16-bit total. The role of this is when you do the Robertson algorithm, I'm doing an 8x8 multiply, starting with an 8-bit operand, and I'm coming up with a 16-bit product. So initially what I do is I put the 8-bit operand on the bottom, and I put the bottom 8 bits of the 16-bit product on the top, and I make that's why I have this high-low thing. It sounds really silly, that's what I'm doing. Then each time I finish with a bit in my multiplication, I can throw away that bit, right? It's just like doing pencil and paper multiply. So I sit here and I do 1001 times 1101 or something. So initially, my accumulator is going to look like, I start with all zeros, and I got 1101 on the bottom. First operation I do, ooh, I get that guy. I now put him in on the top, and I move everybody down 1, and I don't need that anymore. And so I'm gradually shifting across. And so I start with a 0 of 4 bits, or in your case 8, I think, and then I've got down here 4 bits of operand. By the time I'm done, I've walked the operand off the end, and now the entire field is available for the product. So that's what this does. So all you have to do is just, again, come up with whether to load or hold on these. Know when to load them and know when to fold them or hold them or whatever. Okay, so that's that one. A couple others. Let's look at the muxes. So mux 5, you've got a 3-bit input. You have five different data inputs and a 3-bit control. And it selects which of the 5 gets routed out. So that guy should be pretty easy. And who else is entertaining? Oh, down counter. It either gets loaded, either stalls, or it gets loaded with some number, or it gets, or it decreases by 1 every time. So that's all that does. Always at pause edge clock, fill in the guts. Yeah, so this parameter width 7. So if I'm resetting, I put a 7. And otherwise, I subtract 1. Otherwise, I do nothing. So that's all that guy needs. And what else do we have that's amusing here? Counter down, we looked at that. ROM, you don't have to change. Oh, this is a fun one. This one needs to be able to do either a logical right shift or arithmetic right shift. So it either holds, it has an enable, so it has an input coming in, and I either bring the input in shifted logically, or I bring the input in shifted arithmetically, or I just hold what I've got. So it has an input that's 16 wide, it has an output that's 16 wide. It's always right shifting the input to the output, but the question is, what do you do with the first bit? And that's the arithmetic versus logic. So that's all that one is. Okay, so just get each of those guys wired up. Then I give you the test bench. So go ahead and run it through the test bench. Check your results. The test bench will come back and tell you what works and what doesn't. So in fact, we do a little demo run here. So I'll go ahead and kill this other one.
Also, is the test bench just the thing that's called Robertson's multiplier?
Robertson test. Yep. So if I go here, yeah, if you're still stuck, use office hours and use Piazza. We'll get you through this. Yeah. We will survive here. Recent projects. Let me see if I got oh, there we go. Robertson. This one will work right here. Okay, so here's the project. Here's all the stuff theoretically working. I've already compiled it, so I'm just going to start simulation, pick Robertson test as my top level. And away we go. And then if I'd like to look inside, particularly down inside the unit, down inside the multiplier, I'd like to see what the control is doing maybe, or see what the, if you have any sort of sequential state machine, it's always good to look at your program counter, because that's going to walk you through your program. And this thing has 17 words of microcode in it, or 18, it goes 0 to 17. So I'd like to see what that guy's doing. That's UPC. Let's add him to our waveform. I'd like to see what the data path is up to. How about this big register we just talked about? That's reg-r. Let's add him to our data path. And then we go ahead and run. And see if I can embarrass myself here. Well, almost. Okay. So this tells me that for these particular sets of inputs, again, these are all 2's comp numbers, this 8-bit times this 8-bit, the expected answer was 0, we got a 0. This was 5 times 6, expected answer was 30, we got 30, etc. The only place we had trouble, and I've already told you guys, you don't have to take really large negative numbers, or toward large magnitude negative numbers toward minus infinity. So it does choke on really large negative numbers. So I told you I have to go beyond minus 64 or something. And my test bench doesn't, except for this one case. So these guys all passed. And then what you do is, if something hadn't, like I had a guy in my office today, we went through this because it didn't quite work for him. We wanted to see what was going on. And it turned out he didn't do the shift register quite right. And the way we knew that was that we looked at his answers, and the bottom byte looked good, and the top byte was crap. And so that shift register is what's handling all your sign extension and negatives. And so that's a good symptom. But that's what we did. We started just going through to see where might he be having trouble. And so here you can see that there's our 0 times 0. There's our 5 times 6. And there's our reset that we issue to start each new operation, and the done flag. So there's our handshake. So there's our request. It's reset. Our acknowledge is done. We issue a new reset request. Acknowledge is done. So that's the handshake between the test bench and the actual thing inside. Then we can blow this up and have a look at it. And let's see what's inside here. And multiplier, 5, 6, product. I'm going to do this guy in hex. What the hell? I think I'm going to do everything in hex. Put a hex on everything. Okay. So we can watch what's going on. There's my cycle counter. It's just counting what cycle I'm on. So here's my here's what's interesting. 0 times 0 came back 0. Big whoop. That's really exciting. Wasn't that exciting? It's like watching paint dry. Okay, so let's look at 5 times 6 will be a little more amusing. Remember what I said about this dual size register over here? There's our 5. Doing 5 times 6, there's our 5. Now I've got 605, and let's just step across. And this thing is in my way, but let's go ahead and do this. So there's 605. How do I get from 605 to 305? The top half got right shifted, right? And to 105. So there remember I'm multiplying 6 times 5, which is real simple, 101 binary and 110 binary. So the 5 is on the bottom. There I'm walking the 6 down. So there's my 6, shifted it by 1 bit, shifted it by 1 bit, and then I start pulling together my result. And let's look at where our done flag comes. So our next done flag happens right here. So there's the done flag going high. There's my pop-up timer. So I said, I'm done. Okay, and I keep showing the 5 there, and I put a 1E on this guy, which is the 30 decimal, which is expected. At that point, the test bench is supposed to say, you have a done flag. I am going to read your value. Oh, isn't that cool? So I go ahead and read it here. You've got a 30 for your answer. And then I, meanwhile, did 5 times 6 the easy way, and I got 30. We match. I put out success. We go to the next one. But what I'd watch for on the health, if things aren't going well for you, let me get rid of this extra clock. I don't need that. I would watch this big dual register up here called R, and I'd watch product, and then I'd watch the R register down here, which should look very much like it. Reg R, in, out, clear, out. There it is down here. And now you can see the 3C. What happens to 3C? 78 if you right shift at 3C, if you right shift at 1E. That's our answer. So here is, in fact, here is that reg right here. Okay, F0. F0 right shifts to 78, right? The F goes down to 7, and the 1 on the end becomes the 8. So if I take F0 hex, right, divide by 2 or right shift it, I get 78. 78 right shifts to 3C, right shifts to 1E. I stop because I've counted the right number of cycles to walk through the whole multiplication problem. There's my answer. So if I was not getting this sort of stuff up here, I would want to take a good hard look to see if something's choking on that. The other thing you can do, green is good, red is bad. So you want to make sure, and if you've got any vision impairment on red-green, look for X for the reds. I keep telling my tool vendors that you use red and green for the important stuff, and 10% of my students have trouble with this. 10% of the male students have trouble with this. So anyway, what you do though, you look for anything that says red or says X is bad. And the only time you should ever see a red, back here I got red, but these guys have X in them. This is before I'm done with reset, or this is very early in the game. But you notice once I'm past here, you don't see any more red anywhere. Everything else is clean. The guy who came in at office hours was talking to me today. He was showing red at various places, and so you play TV repairman. And the way TV repairman works, in the old days before everything was on one integrated circuit, you had a big circuit board and you passed signals from here to here to here. And so if you lost your signal, you'd either start at the end where there's no signal, work your way back up the schematic till you found a signal and see where you lost it, or you can start at the front where you had a signal until you lost it, whichever way you wanted to go. Same idea here. If I see a red, what block gave me a red? Which block's output is red? What were that block's inputs? Because one of them was probably red, or it did something really stupid. Then you can sort, if its inputs are all green and it puts out red, you got a bad block. You dive in and find what's going on. If one of its inputs is red, that's probably why its output's red. If your inputs are not happy, you're not happy, and your outputs aren't happy. So then you work back and say, well, who made that? That must have been somebody's output. It was nobody's output because you forgot to hook it up. Okay, we'll hook it up. So you do that sort of stuff. So that's how you play the game. So this guy can really be your friend. Your alternative, and some of my real hardcore software people do this, is to write a whole bunch of diagnostic print statements all over the place. But this is quick and dirty. If you want to, you certainly can. We just call it display instead of print. But I mean, you can put $display anywhere you want to. But this is probably pretty good too. So that's what we look for. So I hope that somewhat helped. And then just look at these exact examples, like the ones I gave today, showing you how to do the little simple state machine, because you need state machines all over the place. We've got them inside the multiplier to tell. Typically, the story is you'll have some arithmetic or logical data path that chews on data, and there will be something that tells it what to do or how to chew. And that's going to be a state machine, almost always. So almost everything has that in it, or the whole design is a state machine, like our traffic controller. And so we're looking at those. And then just the general rules. I showed you a couple of sequences today with PowerPoints showing you typical good design rules. And this website is still about my favorite. If you just go to these guys. They're insecure. Okay, tough. We go to System Verilog. And we just go right to the examples, if you like. Decoders, muxes, flip-flops, state FIFOs. Or there's a good tutorial you can work through as well. Verilog basics, control statements, if, else, and while, and tells you all this. And you can download any one of these and try it out yourself, which is really a good thing to do. Try building it, look at it on the waveform viewer, wrap it in a little test bench, put a display statement, see what it does. This is a really good way to get comfortable with the language. Initial blocks. Initial begin, we put everybody at 0, okay? Or whatever value we want to initialize. And these are the always blocks that we had. So there's the System Verilog. But these, I don't know, I find trying to learn a language, sometimes just looking at people's examples. You got up-down counters, gray counters, one-hot counters, divide by 2 counter, divide by 4.5 counter. If you want to know how to do a divide by 4.5 counter, there it is. And so you can do stuff like that. So does that help any? Yeah. So work through that and take advantage of the office hours in Piazza. We'll get you caught up on everything. And somebody let me know immediately if the podcast didn't record today, because I'm going to kill somebody. No, I didn't say that. Anyway.
Actually work with IT, so
Okay. So they tell me the audio's off. What happened is they revamped this room completely, and they forgot to hook up the audio DSP, so that you saw the note on that. So I apologize for them. But, you know, in Russian, they say, "Это бывает," it happens. And we have a similar expression in English. Okay, all right, yeah. Anybody else? You're good? You're good? You're good? Everybody good?
for now.
For everybody good for now? Okay, all right. Okay, anything we can help you with, let me know.
This has been a UC San Diego podcast. For more, visit podcast.ucsd.edu or 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 visit podcast.ucsd.edu.